Hello everyone, welcome to this lecture. So, we will now start shifting our attention to other topics, other problems in secure distributed computing. Remember that our eventual goal is to design secure multi-party computation protocols tolerating malicious corruptions. Towards that goal, we have already spent quite a lot of time discussing Byzantine agreement and broadcast protocols. We will now start looking into some other primitives which will be useful for designing MPC protocols. Before going into those primitives, we have to brush up our knowledge, whatever information we have regarding abstract algebra. So, I will be quickly going over some of the topics from abstract algebra which we will require. So, in this lecture we will touch upon the basic properties of groups, rings and fields. So, what is a group? It is some set with a binary operation. The set could be finite or infinite. It has some binary operation which I denote by O. So, which operates with two operands, and the set G along with the operation small o will be called as a group if some properties are satisfied. These properties are also called as group axioms. So, the first axiom is that the operator O should satisfy the closure property, namely if you perform the group operation with any pair of elements A B, including the case where A and B are same, then the result should be an element from the set G itself. The second property is the associativity property, which demands that the operation O should be associative. That means, it does not matter in what order you do the group operation, you do the operation with involving A and B first and then involve C, the result should be the same as what you obtain if you do the group operation over B and C first and then with the result and the operand A. Yeah. This should hold even if A, B, C are identical, they are different, so on. There should be a special element, a unique element small e from the set G, which we often call as the identity element, such that you take any element A from the set G and perform the group operation with E, you should get the element A only, and this should be the case for every element small a in the set G. And the fourth property is the existence of the inverse, which demands that you take any element A from the set G, corresponding to that there should be some element denoted by A power minus 1, such that the result of the group operation between A and A power minus 1 is the identity element. If all these four properties are satisfied, then the set G along with the operation O is called as a group. So, few things which we have to note here is that the operation O need not be commutative, even though it is associative. That means, the result of A operation B need not be the same as the result of B operation A. And this notation A power minus 1 is just a notation. Okay. You can use any notation, say big A, whatever you are comfortable with. It should not be interpreted as 1 over A, that is not the case. Let us see some examples of groups. So, imagine n is a positive integer and I denote a set Z sub n, which is the collection 0 to n minus 1. So, you can imagine that this is the set of all remainders modulo n. That means, you take any integer and you divide it by this number n. So, this n you can imagine as a modulus. So, you take any integer and divide it by this modulus, you will get a remainder in this collection Z n. So, now in this set Z n, I define an operation which I call as addition modulo n, denoted by these notations. Under plus we have this subscript n, and the result of this operation is a plus b modulo n. That means, you add a and b, that is a regular addition, but that is not the answer, that is not the result of a plus b modulo n. The result is the modulus which we obtain after dividing a plus b with n. Now, the claim is that the set Z n along with the operation plus modulo n constitutes a group. So, my Z n serves the role of big G, and this operation plus modulo n serves the role of operation O in the previous definition. Let us see whether all the group axioms are satisfied or not. So, the first group axiom is satisfied because you take any two remainders A and B from the collection Z n, you add them and take modulo n, you will again obtain a remainder R, which will be a number in the range 0 to n minus 1. So, the closure property is satisfied. The operation addition modulo n satisfies the associativity property, because it does not matter whether you do first A plus B modulo n followed by C modulo n, or you first do B plus C modulo n and then to that you add A and do modulo n. The result or the final remainder will be the same as what we get by adding A, B and C and then taking modulo n. So, the associativity property is satisfied. The element 0, the integer 0 belongs to the set Z n, and that serves as the identity element E, because if you add 0 to any element A from the set Z n, the result will be A only, and the effect of mod n will not be there, because if A is less than, if A is Z n, then A is strictly less than n. And corresponding to every element small a, I can define an element minus a, and my minus a is nothing but n minus a here, which is the inverse of the element a, because if I add minus a to this a and take modulo n, the result will be n modulo n, and n modulo n will be the 0, which is the identity element. So, minus a will be the inverse of a. So, that means this collection Z n along with the operation addition modulo n satisfies all the group axioms. Now, let us see another group. Okay. I define now a set Z n star, where I take only those elements from Z n which are co-prime to my modulus n. That means, the GCD of that A and my modulus n is 1. And now, in this set I define a variant of the multiplication operation, which I denote by this notation dot subscript n. This is called multiplication modulo n operation, and let us see how do we get the result of multiplication modulo n operation. So, if you want to apply this operation on two numbers a and b which are from the set Z n star, then you first do the regular multiplication, regular integer multiplication, you multiply a and b, but that will not be the answer. The answer will be what you get after you do a mod n. And now we can prove that the collection Z n star along with this operation multiplication modulo n is a group. It satisfies all the group axioms. So, now in this example my set big G is Z n star, and my abstract operation O is the multiplication modulo n operation. So, let us see whether all the properties are satisfied or not, all the group axioms to be more specific. So, closure property is satisfied. To prove the closure property, let us take two arbitrary elements A and B from the set Z n star. So, that means individually A is co-prime to n and B is co-prime to n. We want to show that A multiplied with B modulo n is also an element of Z n star. Okay. So, imagine that A multiplied with B modulo n is R. We already know that R is in Z n because R will be a number in the range 0 to n minus 1 because we are multiplying A and B and then taking a mod n. So, definitely the mod will be either 0 or 1 or n minus 1, but that is not our goal. We want to show that R is a member of Z n star. We want to show that GCD of R and n is 1, and that is very simple to show. Since A and B are relatively prime to n, they are individually co-prime to n, then so will be AB. Because if AB is not co-prime to n, then that implies that either A is not co-prime to n or B is not co-prime to n, but we are assuming that A and B are individually co-prime to n. And what can we say about the remainder R here? Remainder R is what you obtain after dividing AB by n. That means, it is the result of subtracting some multiple of n from AB for some k from the set of integers. So, now if the GCD of R and n is not 1, then we basically end up showing that the GCD of AB and n is not 1, which is a contradiction, because the value of R is this and k times n is completely divisible by n. So, if at all the GCD of R and n is not 1, that means the GCD of AB and n is not 1, but that is a contradiction. So, that shows that the closure property is satisfied. The operation multiplication modulo n satisfies the associativity property. It does not matter in what order you perform the operation multiplication modulo n involving 3 numbers A, B, C from the set Z n star, the result will be same as the product of A, B, C modulo n. The integer 1 is a member of Z n star because 1 is always co-prime to n. And it serves as the identity element because you take any element small a from the set Z n star, you multiply 1 with a and take modulo n, you get the number a only, because since a is a member of Z n star, it implies that a is strictly less than n, and that is why a modulo n will be a only. And if we take any element a from the set Z n star such that the GCD of a and n is 1, it is coming from the definition of Z n star, then there is a very well known algorithm in number theory called as extended Euclid's algorithm. It is basically just extension of the simple Euclid's GCD algorithm, recursive Euclid's GCD algorithm. It is an extension of that algorithm which allows you to find out another number b from the set Z n star corresponding to this number a, such that a b modulo n is 1. So, b will be the inverse of a. Okay. So, let me demonstrate this group Z n and Z n star with an example. If I take n is equal to 6 and then if I take the operation plus modulo 6, then here is the group table. Along the rows I have the elements of Z n, Z 6 here 0, 1, 2, 3, 4, 5, and along the columns also I have the elements of Z6, and now we can fill the table. So, 0 plus 0 modulo 6 will be 0, 0 plus 1 modulo 6 will be 1, 0 plus 2 modulo 6 will be 2, and like that 0 plus 5 modulo 6 will be 5. The next row will be 1, 2, 3, 4, 5, 0. So, for instance, 1 plus 4 is 5, 5 modulo 6 will be 5, but 1 plus 5 will be 6 and 6 modulo 6 will be 0. So, like that you can fill the other rows as well. And now you can see the closure property is satisfied, because in this table none of the elements are from outside the set 0 to 5. All the elements are from the set 0 to 5 only. The operation plus modulo 6 is anyhow associative. The element 0 is the identity element, because if you see the column under 0, then 0 addition 0 is giving you 0, 1 addition 1 is giving you 1, 2 addition 0 is giving you 2, 3 addition 0 is giving you 3, 4 added with 0 modulo 6 giving you 4, and 5 added to 0 modulo 6 giving you 5. That is the additive identity, namely the element 0 is the identity element, and now let us try to find out the inverse. Okay. So, inverse of 0 will be 0 only, inverse of 1 will be 5, because 1 added to 5 gives you the identity element 0. The inverse of 2 will be the element 4, the inverse of 3 will be the element 3, the inverse of 4 will be the element 2, and the inverse of 5 will be the element 1. So, you have the inverse present as well. In the same way, I can draw the table of group table for Z7 star. I can take n equal to 7, and then I can fill the rows and the columns, and then you can check whether all the properties are satisfied or not. Now, let us go to our next algebraic structure, which we call as ring, and now we have a set with two binary operations denoted by plus and dot, and they are not regular addition and multiplication operations. They are not the regular addition and multiplication operations. So, in fact, you could have used the operations O1 and O2, but typically in textbooks we use the operation plus and dot to denote the operations O1 and O2. So, now we need some properties to be satisfied with respect to the first operation, namely the plus operation, and some properties should be satisfied with respect to the second operation O2 or the multiplication, so that the underlying algebraic structure or the set R along with these two operations is called as a ring. So, the first property is that if I take the plus operation in the set R, that should constitute an abelian group. Now, what is an abelian group? Well, it is a group, that means the closure, associativity property, existence of the identity element and existence of inverse should be guaranteed. On top of that, the operation plus should be commutative. If that is the case, then we say that the set along with the operation is an abelian group. Okay. Now, notice that here to denote the identity element with respect to the plus operation, I am using the notation 0. This need not be element 0, this need not be integer 0. It is just an abstract notation. In fact, you could have used the notation E sub 1 to denote the identity element with respect to the plus operation. and in the same way this element minus a is not the negative a in the sense that it is not the minus of integer a, because element a is an abstract element from an abstract set, it need not be always an integer. Okay. So, that is the first property. The second property is that the second operation, namely the dot operation in the set R, should satisfy the closure property, associativity property, and there should be an identity element. Okay. However, existence of inverse not needed. That means closure means you take any pair of elements, you do the dot operation, the result should be an element from the set R. You take any triplets of element, any triplet of elements A, B, C and do the operation dot, the result should be the same, and there should be a special element which I denote by 1, which constitutes the identity element. Again this is just a notation. It need not represent the integer 1, because my set R is an abstract set and its element need not be integers. They could be any my set R could be a collection of matrices, my set R could be a collection of vectors, right, it could be anything. And the third property which we require is that the dot operation and the plus operation, they should be distributive over each other, and namely they should satisfy two distributive laws. This is the first distributive law, namely the dot should be distributive over plus, and this is the second distributive law. If all these three properties R1, R2, R3 are satisfied, then the collection R along with the operation, the abstract operations plus and the abstract operation dot will be called a ring. Okay. So, let us see some examples. The set Zn along with the operations addition modulo n and multiplication modulo n constitutes a ring. So, we have already shown that the addition modulo n operation satisfies the group axioms. Well, it also constitutes an abelian group, because the addition modulo n operation is commutative. The multiplication modulo n operation satisfies the closure property, it is associative, and the identity element will be the integer 1, and it is easy to verify that the distributive laws hold. So, that is why this is an example of a ring. Now, the last algebraic structure which we will be using in this course now is a field, and like ring, field also has a set and two binary operators plus and dot. Again they are abstract plus and abstract dot operators. We will call this triplet a field if the following axioms hold. With respect to the plus operation, the set F should be an abelian group, and now with respect to the dot operation also we require F to constitute an abelian group if we exclude the element 0, which is the additive identity element. If we exclude the additive identity element from the set F, then the resultant set along with the operation dot should constitute an abelian group. So, it should satisfy the closure property, the operation should be associative, there should be an identity element, and every element from this small subset, namely the subset where the element 0 is not present, should have an inverse. and the distributive law should be satisfied. So, if we closely compare the definition of a ring and a field, what we get here is that a field is a special type of ring where every non-zero elements is invertible. And when I say non-zero, I do not mean the values which are different from 0. By non-zero, I mean every element different from the additive identity element, because 0 in this context stands for the additive identity element. So, some examples of field: if we take the modulus P, where P is a prime, then the collection ZP, which will be the set 0, 1 up to P minus 1, is a field. We can prove that, but we will not be going through the proof. And one final property which we require, which holds in the field, which we will require later, is the following: that in the field, if the product of any two elements x and y is 0, and when I say 0, I mean to say the additive identity element. If the product of any two elements x and y is the additive identity element, then either x is the additive identity element, namely 0, or the element y is the 0 element. And this can be proved through a contraposition. Namely, we can show that if x is either not 0 or if y is either not 0, then x dot y is also not 0. Let us see how we can prove that. So, if x is not 0, then x inverse exists, the multiplicative inverse basically. Which is the inverse of the element x with respect to the dot operation. And in the same way, since y is not 0, then there exists an inverse of y with respect to the dot operation. Let us denote it by y power minus 1. Now, what we can say about y power minus 1 product x power minus 1? Well, it is going to be the inverse of x dot y, because if we multiply x dot y with y inverse dot x inverse, then that is going to give us x dot y inverse dot x inverse. Now, y dot y inverse gives me the element 1, and x multiplied with 1 will be x. So, this becomes as x multiplied with x inverse, and x multiplied with x inverse will be 1, which is the identity element. That means, the element y inverse dot x inverse is the inverse of x dot y. But from the definition of field, we know that it is only the non-zero elements which have the inverse. That means, if at all there is an inverse of x dot y, the x dot y has to be an element different from 0, but that is a contradiction, but that is what we want to show through the contraposition. Okay. So, we ended up showing that if either x is not 0 or y is not 0, then x dot y is also not 0, which actually is equivalent to showing that if x dot y was 0, then either x is 0 or y is 0. Okay. However, this property need not be true in a ring. That means, in a ring we can find non-zero x, non-zero y, but their product being 0, that is possible. Okay. And where exactly the proof fails, whatever proof we have given for the case of field, the proof fails down because we use the fact that x inverse and y inverse exist in the case of field, and that comes from the field axiom F2, because if x is not 0 and y is not 0, then as per the definition of field or axiom F2, x inverse and y inverse exist. But if we take a ring instead of a field, then the ring axiom R2 does not guarantee us that x inverse and y inverse exist, because in ring It is not necessary that every element has a inverse with respect to the dot or the multiplication operation. So, these are the basic things regarding our abstract algebra, which we will be using now for the rest of the course. There are several well known references to know more about abstract algebra, groups, rings and fields. I have followed the discussion which is available as part of the NPTEL lectures on discrete mathematics course offered by me. Those videos you can access from this link. Thank you.